So in this last third of the lecture, I'm talking about memory. So let's talk about memories. Well, maybe not about these memories, but about these memories. So, what could we say about memories? Well, for memories, we do have the same issues again that we also have for the processors. For the memories, efficiency is again a concern. And that means that we have to take into account the capacity of the different memories. We need to care about the energy efficiency of memories. We need to care about the speed, both in terms of the latency and the throughput. And also for real-time systems, it's more important than for PC-like systems that we have a predictable timing. And of course, the size, the cost, and other attributes like volatility, persistency are relevant for these memories. Now, first of all, let's have a look at the capacity. I think the capacity of memories is predicted to increase at a very dramatic rate and at a very interesting rate. So if you look at this diagram, which is a diagram published by the International ITRS roadmap effort, so that's the effort that tries to predict the trends in semiconductors. If you look at this map, you see that the highest number of bits that's predicted will be achieved for so-called multi-level flash cells. With multi-level flash cells, we are storing a number of bits in each of the transistors, and if you look at this part of the diagram over here, you can figure out that it is predicted that these multi-level flash chips will lead us to close to 1 terabit per chip, which I think is a very impressive number. You can also see that other high densities are obtained with using other types of memory technology, like for single level flash chips, we have a lower density there. These red triangles, they correspond to single level flash chips, which means that we will be storing only a single bit there per transistor. And also for DRAMs, we see that we are expecting a very strong increase in the capacity. So the exponential increase in the memory capacities that are predicted is expected to continue. So in this way, referring to the capacity as the objective, we expect to have a strong increase in the future there as well. Next, I'd like to look at the energy and power consumption. We can try to, first of all, estimate whether or not the power consumption in the memories is really relevant, or whether it's feasible just to restrict to the energy consumption in the processes. Again, I'm referring to the International Technology Roadmap for Semiconductors. I'm referring to one of the most recent updates there. And according to that update, we can look at the power consumption of stationary systems. So that means the two PC-like systems. There we see the different contributions. We see the contributions for logic, both the switching power and the leakage power, and also we see the contributions for the memory, again both the switching power and the leakage power. If we just look at the power consumed by the memory, we see that there is a good contribution there of the overall power consumption. However, the power consumption for the logic in a standard PC is actually dominating. Furthermore, it's, I think, really interesting, at least, to see the overall power consumption. The overall power consumption over here is predicted to be in the area of well beyond 450 watts. which is a value predicted for an average PC, and I think that is really a nightmare if you consider the overall energy consumption that's resulting from the use of billions of PCs then over the world. So therefore, I'm not really sure whether we should all go for this really large power consumption. With respect to embedded systems, it may be more interesting to look at consumer portable systems. So in this case, we look to kind of smartphones. I mentioned that I include them as a special case of an embedded device. And there we can see that the overall power consumption for the memories has really a larger share of the overall energy consumption. So therefore, for these portable devices, the energy consumption in the memories is actually more important than for standard PCs. With respect to these predictions and with respect to these forecasts, there is one very inherent problem. And this is a problem that for a portable system, we can hardly consume more than half a watt to maybe to up to 1 watt. Otherwise, the battery will not last very long, and otherwise we will very easily burn our fingers on the smartphone, and I think it's so far considered unacceptable that we have to add a fan to smartphones. Just think of having a smartphone that is 3 millimeters thick and that has to include a fan in these 3 millimeters. So I think that's completely impossible. Even if thickness would be increased to 5 or 6 millimeters, I think it would still be rather difficult to add a fan there. Currently, it's not yet known how we can cope with that constraint, and some new techniques are required in order to meet that constraint. Also, this diagram tells us that the contribution of the memories to the overall energy consumption is significant. This means that even if we take into account the RF part, if we take into account other peripherals, and if we take into account the audio amplifiers and the display, even if we take all these components into account, the memories are still in charge of a major share of the overall energy consumption. So this motivates a closer look at the energy consumption of the different technologies that are available for implementing memories. Most notably, we can use a static RAM and we can use dynamic RAM. Static RAM cells are larger, but they provide a faster access, at least as long as they are not too large. Whereas DRAMs are smaller and therefore they allow us to implement larger capacities. If you look at the energy consumption over here, that means at this line and at this line, you see that the energy consumption of both types of memories is increasing with the size of the memories. So that means, in a way, small is beautiful for memories, because the smaller the memories, the less energy we burn per access to the memory. And the reason is that small memories have rather short lines, so therefore the capacitances are rather short, and therefore accesses to small memories are more energy efficient than accesses to large memories. Also, you can see that we have a similar observation there for the access times to these memories. The larger the memories, the more access time we need per access to these memories. The fact that these times increase with the size of the memory has also been observed earlier. So it has been observed, for example, already in 2001, and it has been observed for other types of memories. For example, this also applies to multi-ported register files, and there you see that the cycle times also increase if you have a larger number of registers there in your register file. Obviously, the area does also increase if you have a larger register file, and the power consumption also increases with the number of registers. Now, with respect to the speed, that means continuing the arguments about the speed, it has been observed in a report that was published in 2002 that the speed of DRAM has been improving over the years only in a very limited way. Was observed that the speed of DRAM improved only at a rate of 7% per year. I spoke to a memory designer and he said, yeah, that's certainly true, because our key target is to increase the capacity, and a Forrester access is just considered as a side product, but the key target is to increase the capacity. Then furthermore, we can also look at the overall performance of processors, and we can see how these processor performances are increasing. For quite a number of years, processor performances have been improving at a rate of 50 to 100% per year, which means that this gap doubled after at most 2 years, which means that the gap between the speed provided by the processors and by the memories has been increasing over the years. Now, this was an observation that was made for standard PC-like applications. It could be different for MP-SOCs, where the memories and the processors are implemented on the same chip. However, it can be observed that also for MP-SOCs we do have the same problem. We do have the problem that the memory access times are becoming a lot larger than the processor cycle times, and therefore we have to cope with the so-called memory wall problem. The memory wall problem means that we might find ourselves in a situation where we try to find a path towards higher performances, and then quite unexpectedly we find ourselves blocked by a wall which we did not expect there. So therefore it's very important to address this problem of the memory wall. Now, to be serious, I have to admit that the clock speeds of processors have not really increased over the recent years, that clock speed increases have come to a halt. You can see this in this diagram taken from the book of Hennessy and Patterson. And there you see that clock speeds have essentially increased to the year at which this report published on, or this report cited on the previous slide was published, and after that year, after 2003, clock speeds have increased only in a very limited way. Now, I have to admit that the speed gap in this way is not widening anymore. However, it's also not getting larger anymore. It doesn't disappear, though. We still have to cope with the fact that we have this speed gap between memories and processors. Now, in order to cope with the speed gap, the use of memory hierarchies is rather widespread. The use of memory hierarchies rather frequently implies the use of caches, where I think the set associative cache is the most popular type of caches. With a set associative cache, we are trying to figure out whether or not the information related to a certain address is actually stored there in the cache. And we use a certain set of bits there to address a particular line there in the cache, and then for a particular line there in the cache we read out the tags in all the sets that are available there for that cache line, and for each of the sets we are comparing the tags with the corresponding bits there in the address, and in that way we try to figure out whether or not we have a hit there. In that way we try to achieve a situation where almost all the time we find the information that we need there in these smaller memories, so that as a result we have a rather energy efficient access to the information that we are looking for, and that we also have a very fast access. However, there is a disadvantage. There is a disadvantage that we need to read all these texts in parallel, which means that there is a certain penalty in terms of the energy which is required for reading these texts. Now, in order to avoid this overhead of reading several texts in parallel, we can try to use a different type of memory called the scratchpad memory. Now, what's a scratchpad memory? A scratchpad memory is a small, physically separate memory which is mapped into the address space. So somewhere in our address space we have these addresses that are referring to the locations that we have there in the scratchpad memory. It's very essential that the scratchpad memory is a physically separate memory, because otherwise we will not be obtaining this energy advantage that's resulting from the use of small memories. So this scratchpad memory is placed somewhere between the main memory and the processor, so we might find this in a position where in other organizations we might be using a cache, for example. Accessing values there from the scratchpad memory is done in a very easy way. We just have to use the addresses corresponding to the addresses of the scratchpad memory, and then we will assume that there is a rather simple address decoder which is decoding some of the more significant bits of our address, in this way generating a chip select signal, and with this chip select signal we are then indicating that we have a reference there to the scratchpad memory, and in this way we can be reading and writing from the scratchpad memory. And it's important to realize that this address decoder over here is really a very simple piece of hardware. So one possible question may be the question, well, scratchpad memories may be nice, but are they actually existing in practice? Well, they are existing in practice. There are an increasing number of processors that can be combined with scratchpad memories. For many years, ARM processors allowed the tight integration of so-called tightly coupled memories, which are nothing but scratchpad memories. And more recently, the IBM Cell processor was equipped with scratchpad memories. There is one processor that is very popular in the automotive industry, and also we are observing that for many of the more recently announced multi-core processors, there are scratchpad memories available because standard caches are just too inefficient and are just too costly to implement. So with these very nice scratchpad memories, we do have a number of advantages at the same time. Since these memories are rather small, accesses to these memories are energy efficient. They are also fast, and typically we use them in such a way that we know whether or not we have an access to the scratchpad memory or maybe some other memory, and in this way we also have timing predictability. Now in our lab we tried to figure out by how much we could reduce the energy consumption by using such a scratchpad memory, and therefore we used one of the boards that was available in our lab. We cut the power lines and then were running very long sequences of identical instructions and tried to figure out by how much could we reduce the current required for this board if we were able to move, for example, a load instruction to the little scratchpad memory, which in this case is an on-chip memory. It's implemented on the same die as the processor itself. And we could demonstrate that by moving both the instruction and the data that we are loading there from the memory implemented as separate memory to this on-chip memory, we were able to reduce the current by a factor of 3. And it turned out that the savings in terms of the energy reduction are even larger, because it takes longer to access a particular word there from the external memory. So therefore the savings in terms of the energy consumption was by a factor of 7. So if these scratch pads are very nice, why then don't we just use a cache? Because the key argument in favor of scratch pad memories is the fact that they are small and that they are therefore fast and energy efficient. Well, this is indeed true, but as you can see from this diagram, it's even more true for scratch pad memories, because the parallel accesses that we have for set associative memories need some energy. And you can see over here that for a two-way set associative cache, we would be accessing two of these sets in parallel, and that means we are burning the energy for two such accesses that are performed in parallel. And it also means that the more tag bits that we are using in our system, the more energy we are actually burning, and therefore, yes, the cache is more energy efficient than the main memory, but the scratch pad is even more efficient than the cache. Also, this slide very clearly demonstrates the effect of the associativity. That means the number of ways that we have in such a set associative cache. You see that the more sets or the more ways that we have in a set associative memory, the larger the overhead. Only caches that have just a single set are getting rather close to the energy efficiency of scratch pad memories. However, these so-called direct map memories that just have a single set are not free of strange behaviors, so you can have a very high chance of conflicts between data and instructions, and therefore you can have a very poor behavior of these direct map caches rather easily. So this overview over the memory technology, rather brief overview over memory technology, concludes the section on memories, and this now leads to the overall summary for today's lecture. I started today's lecture by continuing to look at processing in cyber-physical and embedded systems. I explained the key idea of VLIW and EPIC processes, and we saw that using the key idea we can indeed improve the energy efficiency. Also, I very briefly looked at microcontrollers and MPSOCs. And then I introduced FPGAs as one target technology that can also be used to implement systems in a rather efficient way, and in order to find a good compromise between flexibility and efficiency. And finally, in the last third of this lecture, I talked about memories, and there we saw that we could say that small is beautiful if we think of memories, because small memories will allow us to work with a very small energy consumption, with fast access, and also obviously the sizes of small memories are rather small. So this concludes today's lecture. Thank you very much.